Heat treatment is the process of heating and cooling metals to change their microstructure and to bring out the physical and mechanical characteristics that make metals more desirable. The temperatures metals are heated to, and the rate of cooling after heat treatment can significantly change metals' properties. The most common reasons that metals undergo heat treatment are to improve their strength, hardness, toughness, ductility, and corrosion resistance. The amount of carbon present in plain carbon steel has a pronounced effect on the properties of a steel and on the selection of suitable heat treatments to attain certain desired properties. It can change a material's mechanical properties and it aids in other manufacturing steps. It relieves stresses, making the part easier to machine or weld. It increases strength, making the material ductile or more flexible. It introduces wear-resistant, hardness, characteristics, either just to the surface or right through the part. It improves brittleness. Some metals can become weak or brittle once exposed to a specific environment, so they need to be treated in order to overcome this. It can improve the electrical and magnetic properties of a metal, which will improve its compatibility with other materials. There are 3 stages in heat treatment process. The first one is heating, then soaking, and finally cooling. Heating is the first stage in a heat treating process. It is done to change the structure of alloys when heated to some specific temperature. The alloy is said to be at room temperature either by a solid solution, a mechanical mixture, or combination of both. In a solid solution, 2 or more metal are used on each other to form a solution without showing their elements even when checked with microscope. While in mechanical mixture the elements and compounds are clearly visible and compacted by a matrix of a base metal. Soaking is the stage at which the complete part of the heated metal completely changes in its structure. The mass of the metal will determine the time it will be soaked. In other words, soaking is when a part of a metal evenly becomes red due to it been subjected to heat for some time. The third stage of heat treating process is cooling. It also changes the structure of the soaked metal from one chemical composition to another due the way it has been cooled either by quenching or by still air. None of the 3 stages of heat treating can be left aside. The heating stage helps in changing the structure of the metal from room temperature until it completely reaches the soaking stage, which is when the metal evenly becomes red. The cooling stage is the stage at which the metal completely changes to its new properties due to the cooling process. There are mainly 6 heat treatment process: annealing, normalizing, quenching, tempering, hardening, solution annealing. When annealing steel, the material is heated to a specific temperature, which is predefined by the type of steel being used. Once heated, the material is cooled in a conditioned atmosphere, like the furnace where it was heated. The purpose of annealing is to increase ductility and machinability by improving the toughness of the substance and improving the softness. There are several forms of annealing, like recrystallization, stress relief, spheroidizing process, and full annealing. Each process is designed for a specific function and result. In this process, the metal is heated above its upper critical temperature to change its microstructure. Afterward, the metal is slow cooled. Normalizing is a form of heat treatment that eliminates impurities and improves strength and hardness by altering the grain size to be more uniform throughout the metal. This is achieved by cooling the metal by air after it has been heated to a precise temperature. Quenching is a type of metal heat treatment process. Quenching involves the rapid cooling of a metal to adjust the mechanical properties of its original state. To perform the quenching process, a metal is heated to a temperature greater than that of normal conditions, typically somewhere above its recrystallization temperature but below its melting temperature. The metal may be held at this temperature for a set time in order for the heat to soak the material. Once the metal has been held at the desired temperature, it is quenched in a medium until it returns to room temperature. The metal also may be quenched for an extended period of time so that the coolness from the quenching process is distributed throughout the thickness of the material. Hardened steels are so brittle that even a small impact will cause fracture. Toughness of such a steel can be improved by tempering. However, there is small reduction in strength and hardness. Tempering is a subcritical heat treatment process used to improve the toughness of hardened steel. Tempering consists of reheating of hardened steel to a temperature below lower critical temperature and is held for a period of time, and then slowly cooled in air to room temperature. Why steel need to tempered? Tempering steel after a hardening process allows for a middle ground of hardness and strength. This is achieved by allowing the carbon diffusion to occur within a steel microstructure. When steel is hardened, it can become excessively brittle and hard. However, when not hardened, the steel may not have the strength or abrasion resistance needed for its intended application. Tempering also improves the mach-inability and formability of a hardened steel, and can reduce the risk of the steel cracking or failing due to internal stresses. Tempering is most commonly used following a quenching operation. Heating a carbon steel and rapidly quenching it can leave it too hard and brittle. Tempering it can restore some of its ductility. Tempering can reduce the hardness and relieve the stress of a welded component. Welds can create a localized zone that has been hardened due to the heat of the welding process. This can leave undesirable mechanical properties and residual stress that can promote hydrogen cracking. Tempering helps prevent this. Work-hardened materials often require tempering. Materials can become work-hardened through processes such as punching, bending, forming, drilling, or rolling. Work-hardened materials have a high amount of residual stresses that can be alleviated through a tempering process. Hardening is a heat treatment process in which steel is rapidly cooled from austenitizing temperature. As a result of hardening, the hardness and wear resistance of steel are improved. Hardening treatment generally consists of heating to hardening temperature, holding at that temperature, followed by rapid cooling such as quenching in oil or water or salt baths. The high hardness developed by this process is due to the phase transformation accompanying rapid cooling. Rapid cooling results in the transformation of austenite at considerably low temperature into non-equilibrium products. In the stainless steel, nickel, and titanium alloy industries, the terms anneal, solution anneal and solution heat treatment, are used interchangeably. Alloys of these materials are composed of multiple alloying elements and are solid solutions. By heating these materials up to their solution annealing temperatures, all constituents return to solid solution. In most instances, these elements will not remain in solution as the alloy cools, which is why most materials need to quenched or rapidly cooled to minimize reprecipitation of carbides or other secondary phases. The proper method of annealing, temperature, time, and rate of cooling, depends on the type of alloy. Most austenitic stainless steels are annealed at a minimum temperature of 1900 degrees Fahrenheit 1038 degrees Celsius, followed by water quenching or rapid cooling. Martensitic steels are annealed at lower temperatures, around 1400 degrees F/760 degrees C, and slow cooled.